Good day, let me present a scientific research on the topic, the method of command identification to voice control of the electric wheelchair. In the research, an attempt is being made to develop a prototype of the voice control system for an electric wheelchair, in particular to development the algorithms of the operation of such a system and appropriate methods of processing voice signals to form the necessary command signals, taking into account non-standard and dangerous situations. Thus, the proposed system must necessarily take into account all possible risk factors related in particular to the ability of the system to recognize the patient's voice commands in a certain way, not to be sensitive to registered voice signals similar in value from outsiders, to identify only those voice signals which are actually commands of the system and do not identify commands uttered by the patients in the process on conversations which do not relate to the process of driving a wheelchair. The essence of the voice signals processing methods for the selection of command words and accordingly the formation of control signals based on them is reduced to the following. We need to recognize 4 commands in the voice signals: left, right, back and forward. The work of system was focused on the possibility of working with the Ukrainian language. At the first stage, the user speaks those words into the microphone, the information system processes them and selects informative scenes which will be used to identify those commands in the next step. First, the signal is recorded, then it is filtered using adaptive methods. Next, the word length of each command is determined. At the next stage, each word is segmented into phonemes. Actually, on the last step, areas with signals of vowels and consonant vocalized sounds are determined. All 4 commands differ in their phonetic composition for Ukrainian language. The alternation of phonemes in commands is different. Therefore, for phoneme segmentation, the value of the main tone frequency, which is also the main biometric characteristic of each person, is used as an informative scene. At the first stage, the time limits of each command are identified. For this, a sliding window is used within which the average value of the voice signal is calculated. Further, the value is compared with the threshold, and if it is equal to or exceeds the threshold, then the value of the threshold function is taken as 1 or size 0. The algorithm of such processing is shown in Figure 1a. At the next stage, the main tone frequency is determined, which is present in the vowels and consonant vocalized phonemes. For this, the method of Fermat analysis was used when the main tone frequency corresponds to the frequency of the first maximum in a power spectrum. For this, the processing was also carried out using a sliding window. The algorithm of such processing is shown in Figure 1b. And at the last stage, the command is identified. For this, the known command is processed within the sliding window as follows. The presence of the main tone frequency is assessed. It will be present only in the sections within the duration of the command that corresponds to vowels and consonant vocalized sounds. Further, intervals with the presence of such a frequency are formed, and already by their sequence and size, the command is identified. Since the sequences of those sections and durations must be different for the 4 considered commands. Having identified the commands, generating control signals is not a difficult task. The command recognition algorithm is shown in Figure 1c. A standard computer headset and the Adobe Audition environment were used to select voice signals with spoken commands. Further, the signal was loaded into the MATLAB environment in which its further processing was carried out. The appearance of such a signal is shown in Figure 3. According to the algorithm in Figure 1a, the duration of each command is determined. The view of the value of the threshold function is shown in Figure 4. At the next stage, the value of the main tone frequency was determined. At the last stage, phonetic segmentation of each individual command was carried out. In Figure 5a, the appearance of a voice signal of a first command is shown. Further, according to the algorithm described above, estimates of the spectrum were constructed and its averaging was carried out around the values of the main tone frequency. Processing was carried out within the limits of the sliding window. If the main tone frequency was present within those limits, it was manifested in a signal spectrum. Thus, averaged spectrum values around the main tone frequency were plotted on the same time axis according to where the sliding window was placed. The resulting graph is shown in Figure 5b. Next, a threshold function was constructed with the threshold of 0.1, which was chosen a priori. Its appearance is shown in Figure 5c. In Figure 6, 7, and 8 shows the view of the signal of the next three commands, the graphs of the main tone frequency presence in the signals, and the view of the threshold function. In addition, analyzing the given graphs for 4 commands, we can come to the conclusion that, based on the values of the threshold function and the duration of the commands, their identification and the subsequent formation of a corresponding control signals can be carried out. In order for the system not to be sensitive for similar commands that can be uttered by the patient in the context of a conversation, it is suggested to use certain keywords after the utterance of which the command word must be followed. Also, the second keyword will mean the end of the command. These keywords can be selected by the system user individually but with the lowest possible frequency of occurrence in the speech of the user himself. Thank you for your attention.